In the last video, we defined random variable and mass density function. In this video, I want to talk about the expected value of a random variable, and we'll see that we will use the mass density function in order to compute the expected value. But before we jump into the definition, let's consider a context where we probably have thought of an expected value before. So if I say, suppose a group of students has the following 7 quiz scores. So we'll have a 3, a 5, an 8, an 8, an 8, a 10, and a 10. Then the average quiz score among that group of students is, or can be found by taking the sum of those 7 quiz scores and dividing that sum by the total number of quiz scores. And we would get, in this case, 52/7. So that concept is probably familiar anytime you're talking about an average on an exam or anything like that. But what I want to do is try to generalize this here. We're dividing by 7 because we're treating each student as equally likely, if you will. But what we want to think about here, that we're weighting each student equally, but the score values are not equally weighted, right? In the sense that I see among this collection, if I were to randomly select a score, I would be more likely to select, say, 8 than 3. So another way I could write this exact same notion, but dealing with the fact that I want to focus on the score instead of the student, is in the following way. So we could find the average score by using a weighted average. And what I mean by that is the following. So I could take the score 3, weight it by the fact that 1 out of 7 students had it, take the score of 5 and weight that likewise by 1/7. The score of 8, we had 3 out of 7 students had it, and the score of 10 had 2 out of 7. We get the exact same result, but this is something we can generalize a bit to our situations where we have different outcomes that have different probabilities of occurring. So this leads to what we're going to call the expected value. In order to set that up, suppose random variable x takes on the values, we'll refer to them as x sub 1, x sub 2, through, say, x sub n. Then the expected value of x, which I'll point out can also be referred to as the expectation of x. So the expected value of x is defined in the following way. So we use this capital E with brackets for the expected value, and I'm going to take a sum of every possible value that the random variable takes on, which I can represent as xk here, times the probability that it takes on that value. So this would then have to sum from 1 to n if my possible values are x1 through xn. And to tie this back into our mass density function, recall that that actually gave us the probabilities. So I could also express this as the values that the random variable takes on, xk, times the value of the mass density function when I plug in xk. So to be clear, this is the mass density function for x. And if you look back at the way that we computed the quiz average in the second way, That's that notion of the score values, 3, 5, 8, and 10, and among that collection, the probability that we select a student who had that score. So if we want to do this, use this in an example more like what we saw before, let's flip a fair coin 3 times. And once again, let's let X be the number of heads we see. Then our task here is to find the expected value of this random variable X. So a couple things to start with here. We know we can think about our sample space. So the sample space, again, if I'm thinking about H's and T's, is going to include 2 to the 3 or 8 different outcomes. So I want to first pause by listing out what those 8 outcomes would be. Okay, so that's our sample space. And my goal here is to end up with the expected value of X. Notice that from our formula, we have to be able to identify the possible values that the random variable can take on. That, once again, is talking about the range of the random variable. So if I have to find the expected value, then the first thing I want to think about is the range of the random variable. So the range of X here. So X is counting the number of heads seen in 3 coin flips. That can be 0, 1, 2, or 3. Then I need to be able to find the mass density function of X. And again, the reason being that we're going to multiply each of those values by the mass density. So recall that to find the mass density function of X here, I need to identify P of 0, P of 1, P of 2, and P of 3. So P of 0 would be looking at the outcome where we get all 3 tails, and that's 1 out of our 8 outcomes. And the other extreme, P of 3, would be if all 3 landed heads. Now, for the middle values here, 1 and 2, these are more likely to occur because there are several different scenarios in which, for instance, I can see 1 head. It could be that that 1 head occurs on the first roll, it could be on the second, or it could be on the third, and consequently, we have 3 out of 8 for that probability. And for a symmetric argument, we have the same thing for seeing 2 heads. Again, as a check, I can quickly note that when I add all of these values together, I get 1, as I should. And so that's just kind of a nice check. Sums to 1. And then now we're ready to compute the expected value. So at this point, I can say the expected value is as we defined above. Importantly, I don't have to write it in sigma notation. Here, I just know I need to add up 4 things. I need to take 0 times P of 0 plus 1 times P of 1 plus 2 times P of 2 plus 3 times P of 3. Notice that in computing the expected value, if 0 is ever a possible value, it will never really play a role in the expected value. So 0 times anything will be 0 there. So we're left with 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. So we can write that as 3 plus 6 plus 3. So we get 12/8 or 3/2. So that ends up being our expected value. And I'll point out here a common occurrence. So here I'm finding that the expected value of X is not actually a value that X can take on, right? 3/2 is not listed here in the range of X. And that's okay. I mean, we can see mathematically why that might occur. And so this is not telling us that in one occurrence of this experiment, we expect to see 3/2 of the turn-up heads. Instead, what this is talking about is that if I were to run this experiment many, many times, where I flip 3 coins and then count the number of heads, essentially what this is saying is that in the long run, we would expect to see about half of those occurrences end up heads. So rather than saying what we expect to happen in one occurrence, a lot of times we look at the expected value to give us a better idea of kind of the long run average in some sense.